What if you could move a message without sending it? Teleportation is real, but nothing physical travels. The original vanishes here, the identity reappears there. So what are we actually moving? The state. Alright, let's talk quantum teleportation. It's not what you see in movies. We're not moving matter, we're moving a particle's quantum identity from one place to another. Sounds impossible? Let's ask the hard question. How can information appear elsewhere without crossing the space between? Well, if we're not talking sci-fi, then how does this actually work? Well, let's break down the official protocol, which was first streamed up by Charles Bennett and his team way back in 1993. Here's the core idea. Quantum teleportation is all about moving an unknown quantum state from one particle over to another one. It's not the particle that moves, it's the information. Its precise quantum identity, that is. But here's the catch. To make that work, the original state has to be destroyed. Now, before we dive deeper here, we have to clear up some rules of the road that will help us along this journey. Let's start with rule number 1. First, and this is crucial, it is not faster than light. To finish the teleportation, you have to send some good old-fashioned classical information. Think of it like sending a text message, which of course is limited by the speed of light, so no breaking causality. And second, the original state is always destroyed. This is not a quantum copy machine. You can't make duplicates. So how do you do it? You can think of it as a recipe with a very, very specific set of quantum ingredients. To pull this off, we need a few key players. We've got Alice, who's our sender, and Bob, our receiver. Alice has a qubit. That's just a particle holding the quantum info she wants to send. Think of it as Alice has some Bitcoin and she wants to send that to Bob. So the real magic, the secret ingredient, is an entangled pair of particles. Alice gets one and Bob gets the other. And that creates this incredible quantum link that connects them no matter how far apart they are. Okay, we've got our ingredients. Now we can follow the 5-step protocol that makes this whole thing possible. Here's the play-by-play. Alice takes her message qubit and her half of the entangled pair, and she measures them together. This measurement completely destroys her original state, but it spits out 2 classical bits of data, just a 0 and a 1. She then sends those 2 bits to Bob over a totally normal channel, like a laser. He uses them as an instruction for what to do to his particle, and the moment he applies that final correction, his particle instantly transforms into a perfect replica of Alice's original. Think of those 2 bits Alice sends as a key to a quantum code book. You know, depending on whether she sends 000110 or 11, Bob knows exactly which one of 4 possible operations he needs to apply to his particle. And he does that. Boom. The state is perfectly reconstructed. So what's really going on under the hood? Well, Alice's measurement forces her particles into one of 4 unique entangled states, which we call Bell states. Now, you don't need to parse all the math here. The key insight is this, that each of those outcomes corresponds directly to the specific fix Bob needs to make. That spooky connection is the engine that drives this entire process. So this protocol isn't just some clever trick, it's baked into the fundamental laws of physics. Those same laws also create some pretty serious real-world challenges. So why must the original be destroyed? It all comes down to something called the no-cloning theorem. It's a fundamental law of quantum mechanics that says you simply cannot create a perfect copy of an unknown quantum state. It's impossible. Teleportation gets around this by transferring the state, not duplicating it. The information literally vanishes from Alice's side the moment it appears on Bob's. Now, in the real world, this is incredibly difficult to pull off. Quantum states are ridiculously fragile. The slightest bit of environmental noise, call it decoherence, can just corrupt them. The photons carrying the information can get lost along the way. All of this leads to what's called imperfect fidelity, which means Bob's final state isn't a perfect one-to-one replica of Alice's, but of course, engineers have a brilliant solution in the works: quantum repeaters. These things are basically like relay stations for entanglement. They use a cool trick called entanglement swapping to create new entangled links over really long distances, which lets them overcome signal loss without ever having to measure and therefore destroy that precious quantum information. So all these works in theory have led us to a really profound idea, which is in teleportation, nothing physical actually travels. It's been called a disembodied transfer of quantum information. The potential for a particle to be in a certain state, that's what moves. And as it turns out, that's more than enough to build the future. And this isn't just theory anymore. The protocol was proposed in '93. And by 2017, scientists were teleporting a photon state from the ground all the way to the satellite in orbit. And even more recently, engineers have developed tiny chips that can send quantum signals over the commercial fiber networks we already have in major cities. The quantum internet is slowly but surely leaving the lab and entering our world. So what's the big payoff here? Why does all this matter? Well, for starters, unhackable communication. Any attempt to eavesdrop on a quantum channel would disturb it, and you'd immediately know there's an intruder. Second, it lets us link quantum computers together, creating these incredibly powerful distributed networks. And finally, it opens up entirely new frontiers in data processing and ultra-precise quantum sensing. And all this leaves us with a truly mind-bending thought to chew on. We've basically proven that a particle's identity, its information, can be separated from its physical body. So if a thing's identity can be in one place while its body is somewhere else, what does that tell us about the nature of information itself? Well, that's all for now, guys, on this edge dive. Please teleport down to the comment section, leave your thoughts, and share this video with a curious friend. Thank you for diving in with us.